are going to continue to our course with the next chapter, which is named as the axioms of probability. In this chapter, we are going to solve our first probability questions. Therefore, we are just going to go through an outline where we define the probability function in the first place. Now, in real life, when you are talking about the probability of something, if you are trying to mention about a probability statement, we always talk about the probabilities of events, right? For example, what is the probability of having rain tonight? Or what is the probability of observing a price increase in the common goods? So all of these concepts, in all of these statements, we are talking about the probability of an event. It is therefore essential to define the concept of a sample space, then the concept of an event in mathematical terms. Then we can talk about the mathematical probability function of events. Once we go through defining the concept of an event, we are going to introduce the probability function and a few axioms of probability that we need to believe in, and we need to meet at a common ground. After believing in these axioms, we are going to mention about a few simple propositions of probability which are going to be very useful in our future probability calculations. Finally, in the last phase of our course, we are going to solve a few questions related to the probabilities of events which are defined in the sample spaces with equally likely outcomes. The fact that a sample space has equally likely outcomes makes the probability calculation procedure easier. Of course, this is not a common situation that we observe in all sample spaces, but as a part of this chapter, we are just going to focus on such probability questions. All right, so let's move on. Let's talk about modeling randomness. So let us remind the concept of randomness and what we are calling random. Now, remember, we have talked about experiments in the previous chapter, and the experiments which are not predictable in advance, which means the outcome of the experiment cannot be exactly known before performing and observing it. So these are experiments which are not predictable in advance, and if they exhibit an inherent variation in the outcomes, so what does that mean? When you perform these experiments, there may be a number of possible outcomes as a result of this experiment. So we call such experiments random experiments. Imagine observing the weather condition tomorrow. So what are the possible outcomes in this experiment? The weather tomorrow can be rainy, sunny, foggy, snowy, windy, cloudy. So there are many different outcomes that we may observe as a result of this experiment. And actually, it is not possible for us to exactly know the weather condition tomorrow. Okay, we can only make a forecast about it, which is not 100% reliable. However, we cannot talk about the exact result or exact outcome of this experiment. So such experiments were called random experiments. And we should say that if we are going to develop a model or a real-world phenomenon, we must always take into the account of the possible randomness. So if you are going to solve an engineering problem, for example, if you are going to solve a manufacturing planning in a factory, for example, there is an input for this problem, which is demand, and usually the demand is not predictable in advance. So the future demand of the customers is basically modeled as a random factor. Therefore, in almost every real problem about a real system, there are some input variables which should be modeled as random. Now, how can we create a model for a random input, a random phenomenon? So we can use probability models. What is a probability model? A probability model is a mathematical representation of a random phenomenon. It is just one way of modeling random phenomena, but it is the most known method. Now, we are going to talk about the probability, and as previously said, probability is defined for events. We can only talk about the probability of events happening. And therefore, at this point, let's just forget about the probability for once, and let us define the concept of event in mathematical expressions, mathematical terms. But before that, we need to define the sample space concept first. Now, what is a sample space? Let's consider an experiment whose outcome is not predictable with certainty. However, the set of all possible outcomes is known. Now, what we call these experiments is a random experiment, right? Now, again, we cannot exactly know the outcome of this experiment, but what we know is the set of all possible outcomes. I cannot exactly write down what's going to happen, but what I can write is the possible outcomes, what can happen. So this set of all possible outcomes for a random experiment is called the sample space of that experiment. And we use the set notation to define a sample space, and we usually denote the sample space with capital S letter. Okay, so imagine these experiments. We are just going to provide a few examples about random experiments, and we are going to define their sample space. So imagine our first example experiment as a single coin flip. Now, assuming that this is a fair coin, what are the possible outcomes of this experiment? Either you observe a head or you observe a tail, right? So the sample space of this random experiment consists of two outcomes. All possible outcomes are listed in this set, and the number of elements in the set is equal to 2. Now, let us focus on another experiment, the experiment of flipping 2 coins, okay, or in other words, 2 consecutive coin flips. Now, if you flip 2 coins consecutively, either you observe double heads, or you observe double tails, or you observe the first flip as a head and the second flip as a tail, or you observe the first flip as a tail and the second flip as a head. So these are all possible outcomes of these experiments, and the sample space of this experiment is listed with these outcomes, and it has 4 elements. In other words, number of elements in S, or the cardinality of S is equal to 4. So cardinality means the number of elements in a set. In the third example, we have an experiment which is the toss of a single regular die. Now, the sample space of this experiment consists of 6 possible outcomes, as we know it, because the die has a cubic shape, and in each face of the die, we have an integer from 1 to 6. Therefore, the outcomes are representing the faces of a die, and there are 6 possible outcomes in this sample space for this experiment. So you see, every random experiment has a different sample space, and the number of elements or the cardinality of the set can be different. Now, imagine your last example is the experiment where we toss 2 dice. How many outcomes do we have in this experiment? Now, by the basic principle of counting, the outcome of the first die toss has 6 outcomes. Number of outcomes is 6 for the first die toss, and for each outcome of the first die, the second die also has 6 possible outcomes. Therefore, by the basic principle of counting, 6 times 6, there are 36 possible outcomes for this experiment, starting from 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, so on and so forth. It goes to the second row, 2, 1, 2, 2, 2, 3. It goes to the third row, so on and so forth, until we have a complete list of these 36 possible outcomes to 6, 6. Now, one fact here is some of the students, unfortunately, are getting confused and thinking that the outcome 1, 3 here and the outcome 3, 1 are the same. So if you get a 1, 3 or 3, 1, you always read it as 3, 1. Actually, this is not the case. Now, here we have two dice. Imagine that one of these dice is a blue die and the other dice is a red die. Okay, so 1, 3 is the outcome where the blue die shows 1 and the red die shows 3. And the outcome 3, 1 is the blue die showing a 3 and the red die is showing a 1. So these two outcomes are different. 1, 3 and 3, 1 are different outcomes of this experiment. And another thing that you need to understand at this point, how did we count the number of elements in this sample space? By using the basic principle of counting. So the things that we have learned in the combinatorial analysis chapter are going to be used in this chapter to calculate the number of elements in sample spaces. So we will be using combinatorial analysis concept to count the number of outcomes or the cardinality of the sample spaces that belong to random experiments. Of course, there are some experiments, random experiments, the sample space of which are uncountable. Okay, now imagine the experiment where we measure the hourly lifetime of a newly bought light bulb. So we are purchasing a light bulb and we are starting to use it, and we are basically measuring the total number of hours until it breaks down. Now, what are the possible values that you can observe for this experiment? The light bulb may not work at all. So when you try it for the first time, you can measure its lifetime as 0 hours as well. However, if it starts to work, it can theoretically work for infinitely large amount of time. Okay, and because the duration is a measurable concept, it's not countable, so it is not a discrete value. Because of that reason, we should say that the lifetime of the light bulb can take any real value from 0 to infinity. So all non-negative real values are the possible values for this experiment. So the sample space is defined as the non-negative real numbers, and we know that this set is an uncountable set. The possible values of these outcomes are uncountably many. Therefore, we cannot talk about the number of elements or the cardinality of this sample space. Another experiment is the daily dollar-euro price correlation observed on any day. And of course, at this point, you do not know the definition of correlation. We are going to learn about the correlation concepts. But at this point, we should say that a statistical correlation can only take values between -1 and 1. So correlation is bounded into this interval, and it can take any real value there. Now, though the sample space for a correlation experiment is bounded, again, because it forms a subinterval in real numbers, it has uncountably many elements as well. So the sample space of this random experiment is also uncountable. Finally, imagine we are trying to test the water purity percentage collected from a lake or dam. Okay. Now, of course, when you implement a water purity percentage on any collection of water, you are just going to get a very, very large percentage, which should be very close to 100%. However, since we are talking about a percentage value, we should say that any percentage value can theoretically take any value between 0 and 100. Therefore, the sample space of this experiment, again, consists of real numbers between 0 and 100, not just integers, not just rational numbers, but all possible real values between 0 and 100 can be a possible outcome for this experiment. Again, the possible values are uncountably many for this sample space for this random experiment. So you see, in these last 7 examples, you have seen that there are some random experiments, the sample space of which are countable. There are some random experiments, the sample space of which are uncountable. Now we can talk about the concept of an event. What is an event? Basically, an event is any subset of a sample space. Okay. Now, imagine a random experiment, and for this random experiment, you have defined a list of possible outcomes, which is given in the set form, denoted by letter S. And if you define a subset E for that sample space, that subset is defined as an event. And depending on how many subsets we can define as many events. Basically, an event is a set that consists of possible outcomes of the experiment. Not necessarily all of them. All of the outcomes are contained in the sample space. If you define a set that just consists of some or any or all or none of these outcomes, then it is just going to be a subset of the sample space. Therefore, it is going to be defining an event. When you define that subset E, then you perform the experiment. If you observe any of the outcomes that are contained in subset E, we say that event E occurs. Okay, so for the event E to occur, we need to observe one of the outcomes observed in E. Now, let's just give some event examples. Imagine the random experiment where we flip two consecutive coins. We have already defined that the sample space of this random experiment would contain double head, double tail, head tail, and tail head as a result. So we can determine the number of outcomes in the sample space again by using the basic principle of counting, basically 2 times 2. So we are just defining an event. And this event is qualitatively defined as getting at least one head in 2 coin flips. Now, please check the outcomes listed in the space. In order to say that we have got at least one head in 2 coin flips, which outcomes should you observe? So if you observe a double head, can you say that we have got at least one head? Yes, you can, because we have got at least one head. In fact, we have got 2 of them. If you observe a head tail or tail head as outcome, again you can say we have got at least one head. However, if you observe a double tail as a result of this experiment, then you cannot say we have got at least one head. So in order to say that event E has occurred, you need to observe any one of these first 3 outcomes. Therefore, event E, which has this qualitative definition, is basically represented by a subset of the sample space which contains the outcomes head, tail, and tail head. Now, when you perform this experiment, if you observe any of these 3 outcomes, then you would say event E has occurred. For event E to occur, one of these 3 outcomes should be observed. Let's focus on the second example. We have an experiment where we toss a single regular die, and we know that the sample space of this random experiment contains 6 possible outcomes, integers from 1 to 6. Now let us define event E. Event E is qualitatively defined as the upturned face to show an even number. So when do you say the face shows an even number? When you perform this experiment, if you see 2 or 4 or 6, then you would say the upturned face shows an even number. Therefore, event E is represented by a subset of the sample space which contains these even outcomes. Event F is qualitatively defined as the upturned face to show a greater value than 4. Now, if we observe a 5 or 6, we say that event F occurs. Therefore, these 2 outcomes are going to be contained in the subset that represents event F. As you see, an event is basically a subset of the sample space. And the event G, the upturned face to show neither 1 nor 3 means, if we observe 2, 4, 5, or 6, then we would say event G has occurred. So event G is the subset represented by these outcomes. Now, please notice in this example, we have a subset event E and we have a subset event F. And if you remember your set theory knowledge, if you take the union of these two sets, you are going to get this set G. Therefore, we should say that set G is equal to the union of E and F, and we can define the set operations like union for events as well. Now, imagine your third example is the random experiment where we measure the lifetime of a newly bulbed light bulb, and your sample space in this case would consist of non-negative real numbers from 0 to infinity. Now, we define event E in qualitative terms as the light bulb to work at least for 1000 hours. So how do we define event E as a subset of sample space S? Because the light bulb is going to work at least for 1000 hours, as a lifetime of this bulb, if we observe anything that is greater than or equal to 1000, then we would say event E has occurred. So all lifetimes which are greater than or equal to 1000 are forming the event E as a subset of the sample space. Now, event F is the light bulb to burn out in 1500 hours. Now, which subset of the sample space represents event F? So if you observe the lifetime of the light bulb to be between 0 and 1500 hours, then you would say that event F has occurred. So this bounded subset as a subinterval between 0 and 1500 is forming event F as a subset of the sample space. Now let us define another event G in qualitative terms. It is the event of light bulb to burn out in between the 1000 and 1500 hours. Or in other words, the light bulb should at least work for 1000 hours, but at most work for 1500 hours. Now, the event G as a subset of the sample space should be defined as the real values between 1000 and 1500. So this bounded subinterval in sample space S is defining event G. All of these three events are subsets of the sample space S. Now, please notice that the event E and event F has an intersection, and that intersection is exactly equal to event G. So just like the union operation, we can also define intersection operation for events as well.